Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. And what I'm going to do with this video is I'm going to go back to exoplanets, back to exomoons, and also rogue planets, which are planets that don't orbit stars. Now, I've done a few videos on these with different detection methods, and again, like the previous videos, if you haven't come across what rogue planets are, I'm going to cover what they actually are. I'm then going to cover how they might form, why we think moons might be orbiting them, before we kind of finish on a detection method for this particular video. And this particular video is going to look at the Doppler effect, or radial velocity, which is a technique that we can use for detecting exoplanets, but we can actually apply the same technique to discover moons as well. So let's go back to planets. This one's a fairly obvious one. Most of us will probably agree that planets orbit stars. So a normal planet orbits a star, the Earth orbits the Sun, as do all the other planets in our solar system. Most of the exoplanets we found orbit stars as well. So when we think of planets, that's typically what we see. Just for reference, the planet size and the star size there are obviously not true. They're just a representation, really, of an orbit. Now, there are planets out there that don't orbit stars. They're not gravitationally bound to a star at all. And these are called rogue planets, free-floating planets, or even isolated planetary masses, depending on where you're reading about them or who's discussing them. They may have a few different names. And these are planets that they're just in space. They're not attached to any star. They're not on any kind of orbit around a star, anything like that. So they're quite interesting in themselves, and we do know that they exist. I'm going to show you some examples of those a little bit later on. But how do they actually get there? We know that most planets form around stars. So finding these kind of on their own without stars is a little bit bizarre, or wasn't necessarily expected, but they are there. So one of the possible scenarios to produce them, I suppose, is ejection from an existing planetary system. So planets form around stars, and in the early part, or I suppose later part actually, something happens that causes the planet to be ejected out into interstellar space. There's a few things that can do that. One of those is a close passage of another star. So two stars move past by one another. The gravitational interaction of the second star can destabilize the planetary system, and then it can eject a planet. So that can be one route. Another one is that during the formation process and early on, planets are not on stable orbits. They migrate. They move inwards towards the star, they move outwards. It depends on a lot of different factors. But it does mean that planets can encounter one another. We know from our own solar system that significant collisions can occur. We know that the Earth went through a significant collision in its past. But they can also have close encounters where they actually gravitationally scatter one another. And that can throw a planet out of the system or onto a new orbit. Now, here I've actually put the Jupiter-sized planet being ejected, but in reality, if this was to occur, it would be the smaller planet that gets thrown out of the system. It's always a smaller one. And we do the same thing with spacecraft. We use like gravitational assists around planets to gain energy and essentially slingshot them further out. But you can do that to a planet. You can slingshot a planet out of the system due to a close encounter. Now, we've now got a rogue planet. However, going back to planets in general, we know that most of them have moons. The only exception in our system is Venus and Mercury. They're too close to the Sun, so gravitationally it's not favourable to have moons, so they can't hold on to moons. They're quite small as well. But further out, bigger planets have a lot of moons. The example here is Jupiter and the Galilean moons. Now you can see those with a small telescope, pair of binoculars in your back garden quite easily. You don't need great seeing condition to see those. So there's a fairly significant moons quite close to Jupiter, and they just look like little stars in a line near Jupiter. So if you haven't seen those before, definitely try and have a look at them. So Galilean moons are quite important for this topic. So, can these ejected planets actually keep their moons? So let's say Jupiter gets scattered out of our system. It's got lots of moons. What happens to its moons? Well, they can actually keep their moons. It depends on a few different factors, but basically moons close to the planet can actually be retained by the planet, so they get ejected out and they still have their moons. So that's quite interesting. You've then got these free-floating planets that are able to keep their moons. It's going to be things like the Galilean moons. So those Galilean moons of Jupiter will survive. They're close enough to Jupiter that Jupiter has dominance over the gravitational field force. Essentially, it holds on to them gravitationally. The star is not able to strip them during the scattering process, or the planet it encounters can't strip them either. However, the moons that are much further out are going to get lost. They're too far away from the planet. The gravitational force from the planet is actually significantly less, so it's very easy to actually strip those away. So those outer ones, like the retrograde ones going the wrong way, the smaller ones further out, they would not survive. Now what happens to them? Well, they get ejected from the planet and they could actually end up on orbits around the star and remain in the system. They would then be new asteroids, new minor planets, and if they're big enough, they could actually be planets themselves as well. Because if we put Earth on an orbit around Jupiter, it would be a moon, not a planet. So if you've got a very large moon around one of these planets and it's stripped away from it, orbits the star, it could actually be a new planet. Or all of those objects, those moons, could be thrown out into interstellar space and they then become new rogue asteroids, comets, moons, things like that, or planets, as well as the main planet itself. Now, the second mechanism that could potentially form one of these free-floating planets is from a collapsing cloud of gas and dust, in the same way that a star would form. So what happens here is you have a cloud of gas and dust and it undergoes a gravitational instability. So it starts to collapse under its own gravitational force, and if it's not big enough, it doesn't get hot enough in the centre to start fusion. So it never becomes a star, but it would become a large planet instead. So it could become a gas giant. And this just happens on a smaller scale in comparison to the actual star formation. Same sort of idea, just smaller scale. Now, the interesting thing here is that during that process, it would end up having a disk forming around it, a circumplanetary disk, which is actually where the Galilean moons of Jupiter formed as well. They formed with Jupiter, and during the formation of this rogue planet, you can get moons forming in a disk around it as well. So now we've got two routes to form one of these planets, free floating in space. Both of those have the potential to have moons. So we've got rogue planets that could have rogue moons around them as well. So now we need to actually find them and detect them. We've found lots of exoplanets. The rogue ones, not quite so many. So we've found thousands and thousands of exoplanets, and I suspect about 10% of those thereabouts are rogue planets. These are planets without stars. So there's a smaller fraction of those, but there's still lots. We haven't really got any rogue exomoons yet. I think there's a few candidates, there's a few signals that could be attributed to moons around these rogue exoplanets, but I don't believe they are strong. They're not confirmed quite strongly, if that's the right way of saying it. So we need to actually find ways of detecting those. But first, how do we actually know they're there? I said that we've got hundreds of them, essentially. So James Webb Space Telescope has imaged the Orion Nebula fairly recently in the infrared. Infrared is important for planetary science or any kind of work with planets, because planets emit in the infrared part of the spectrum a lot stronger than stars do. Stars are higher energy, they're emitting at different wavelengths. So if you look in the infrared, these planets actually stand out easier, and so do the disks around stars and stuff like that. So when James Webb actually did this, it managed to find lots of actual planets. Now here in the Orion Nebula, you've got a protostar with a disk around it, and this is quite reminiscent of what's going off on a more broader scale in the entire nebula itself, because it's a stellar nursery. So you've got lots of stars forming there. In fact, if you look at the background image, you've got bright blue stars and lots of other stars with bubbles around them. They are newly formed stars. You've got planets forming around those stars. You've got rogue planets forming. You've got rogue planets being ejected out, and that's how they're being formed. So this is a great location to look for these sorts of objects. Now, here is an image of some rogue objects taken by James Webb Space Telescope. Now, it has directly imaged hundreds of them in this particular area. So these are not inferred from transits or other methods. These are direct images of these actual exoplanets, a bit like how we directly image a star. Now, by the time you watch this video, there's probably thousands of these been detected, because James Webb has been quite prolific and we know where they're likely to form, where they're going to be. So now we can actually expand our studies, and I suspect by the time you watch the video there's going to be way more of these detected. But the interesting thing here is they detected binary objects. So in the boxes zoomed in, these are called jumbos. So let me make sure I get this right. That stands for Jupiter mass binary objects. So these are two Jupiter-sized planets that are in a binary or double planet system. So they're kind of orbiting a common center of mass, the barycenter. They're like a binary star, but a smaller version. And they don't orbit a star. These are still rogue planets. And that poses some really challenging questions as to how they got there. But that's a whole topic for another video. We're interested in the single ones here for the exomoons. Maybe those binaries have moons as well, but it's going to be a little bit more complex to find those. So how do we actually detect them? Because we know they're there, we know they can form, because we've directly seen them. Well, the first method is astrometry. That is the precise measurement of its position of an object. It could be any object really, and you get a coordinate. If you measure that over time, you can look for movement. That movement might indicate there's a second companion there that we can't see, a smaller object which is causing the planet to move around, like orbit. There's a transit method, and that's where an object passes in front of another object, it blocks out some of the light, and then it appears to dim down in brightness. That's how most planets have actually been detected and discovered to date, is the transit method. You've then also got the radial velocity method. This is using the Doppler effect to look for shift in wavelength of light given off by the object. And that's the one we're going to focus on here. If you're interested in the astrometry or transit method, I've done separate videos on those, so go check those out instead. So, what we can do is we can detect an exoplanet by the shift in wavelength from the star. So the star is actually orbiting the barycenter of the system. We can't see the exoplanet, but the exoplanet and the host star are orbiting the barycenter, which is the common center of mass. We measure the light given off, and the Doppler effect will cause a stretching and a squashing, essentially, of the wavelength, and it will become blue shifted or red shifted. It means the star appears slightly bluer and slightly redder, and it oscillates, which relates to the orbital period. Now, I've put here that mass is determined by this method, which is the larger the mass of the exoplanet, the larger the actual Doppler effect on the actual star itself, because the planet itself has a more significant effect on it, essentially. Small exoplanet, lower velocity. So basically you can get the mass from this particular method as well. So here we have the setup. If we've got the star, we can't see the exoplanet, so we can't measure the velocity of the actual exoplanet, but we can measure the velocity of the star, and it doesn't matter on its orientation actually. So with the transit method, we need it to pass in front of the star to detect it. With this method, it can be slightly inclined, and as long as there's some movement, we can still detect the presence of the exoplanet. But we only measure the velocity of the star, not the velocity of the exoplanet. So this is what it might look like. We take the spectrum of the star. As it travels towards us, it gets slightly blue shifted. So the whole spectrum becomes slightly bluer. and when it moves away from us, it becomes slightly redder. Now, we can do exactly the same thing for one of these rogue exoplanets. Because James Webb has actually directly imaged these, we can keep taking images, or not necessarily images, we can take the spectrum of these exoplanets over time, and we can do the same thing. We can look for blue shift and red shift as a function of time, and if there is an unseen moon there, we would expect this shift in wavelength to kind of oscillate. And we can calculate the velocity at each measurement using this particular equation here. So basically your delta lambda is your shift in wavelength. So if we know what our wavelength is, which is the bottom lambda there, quite often we might use the H alpha, which is 656.28 nanometers, and that's when it's stationary. If it moves, it gets shifted one way or another, and that would be your delta lambda. We then got the speed of light, and you can do a calculation yourself then to work out what the velocity might be. So we can basically work out the velocity by just measuring the wavelength of light given off by the rogue exoplanet. And over time, it might look something like this. So what we've got here is on the x-axis, we've got time. Each one of those black dots is a measurement of the radial velocity, that's the velocity line of sight. And this is of a star, but we'd expect the same thing or the same shape from one of these rogue exoplanets if a moon was there as well. So what we can actually get there is the orbital period. So the time between each peak is going to give us the orbital period of the actual moon. Quite easy to do. And then the amplitude, the maximum radial velocity, will also allow us to get the mass of the exomoon as well. So we can essentially use the same technique that we use to discover and detect an exoplanet, but use it on an exoplanet to detect an exomoon as well. So it's exactly the same technique, but it can be quite useful for maybe detecting these type of objects in the future. So thank you for watching. If you enjoy or find the videos helpful, then do consider becoming a member. There's extra videos in the member section. There's also other benefits, but generally it helps support the channel and help make these videos for you. So thank you for watching.